So we are live now, yes?
Yes.
Okay, great. I think it's so we probably should start now. So it's a great pleasure to have today Laurence, who is going to be giving us a talk on deep kernel methods. So Laurence is a lecturer at the moment at the University of Bristol, where he's basically trying to bring together the worlds of Bayesian inference and model deep learning. And previously to joining Bristol, he was a postdoctoral researcher at Gatsby and at Cambridge, where he was mainly working on computation and neuroscience. So very, very happy to have you here. I'm very thanks for for taking the time for doing this, Laurence. So now handle back to you.
Fantastic. Yeah, thanks for inviting me. Right. Fantastic. So please shout at me if you can't see my slides. I'm just going to go on under the assumption that everything's good. So today I'm going to tell you about deep kernel methods, and this is work that I led then with Sebastian Aubert, who's a PhD student in Cambridge, and Adam X. Yang, who's my PhD student now in Bristol. So to introduce deep kernel methods, it's worth going right back and thinking about very basic families of machine learning methods. And so if you think about the first methods that you probably ever learned, they'd be shallow methods. And possibly the first one was a shallow feature-based method, which was linear regression, which hopefully we all know and love. And then there's also a family of kernel-based methods. And these are shallow kernel-based methods, and perhaps the canonical example is kernel ridge regression. And this is kernel ridge regression then is very closely related to the mean of a Gaussian process. So if you're a Gaussian process person, sort of when I say kernel ridge regression, you can just think of a Gaussian process. Okay. And now for good performance in really either of those methods, we need to choose a good kernel function in our kernel methods, or a good feature extractor, a good feature set or basis for that linear regression. Now, if we think about the kernel here in a support vector machine, then the performance of the method is going to change dramatically depending on our choice of kernel and how well that matches the data. So if we choose a linear kernel here, we're going to get a linear decision boundary, and then a polynomial or RBF kernel are going to give us, again, different shapes for that decision boundary, and then different, and sort of these choices of kernel are going to be suitable for different types of data. And exactly the same sort of thing happens in a Gaussian process. So these are samples from the prior of a Gaussian process with different kernels. So this is a squared exponential kernel on the left, which gives us nice smooth functions. And this is a special case of a Matern kernel on the right, which gives us these very rough functions. And some data sets are going to be more suitable for these kernels on the left. Some data sets are going to be basically smooth, and some data sets are going to be rough, and they're going to be more suitable for these kernels on the right. So that's all good, and it works very well for sort of simple data sets, things that you might see in UCI, for instance. But in this brave new world of machine learning, we care now about very, very complicated structured data sets. So things like images on the left or sound here on the right. And the problem here is that you simply can't write down a good feature extractor or kernel for data that's as complicated as this. And that was essentially the key bottleneck in getting good performance using these methods up to the deep learning revolution in about 2012. So the conclusion here is, well, if we can't write down a good feature extractor, then we probably need to learn to sort of specify a flexible family of feature extractors or kernels and then learn them. And that's exactly what deep neural networks do. So deep neural networks then are a special case of feature-based methods because they sort of take input features and transform them into mid-level features and then transform them into higher level features. And they can be thought of as learning a deep, complicated, flexible feature extractor. But now once we've got this grid here, a big question comes up, which is what on earth goes in this box in the bottom right? And the answer, perhaps obviously, is deep kernel methods, but then the question becomes, well, what on earth is a deep kernel method? What on earth might that mean? And so that's what I'm going to talk about in this talk. You know, what might a deep kernel method look like? And I'm also going to talk a little bit about why we might care about deep kernel methods, what kind of advantages they would give us. Okay, then. So to start with understanding how we might get a deep kernel machine, I think it's worth by drawing a really close link, or as close a link as possible, to deep neural networks to really get some inspiration from them. And so we can think about a deep neural network sort of at a very, very high level as taking some data, then putting it into this super flexible learned feature extractor, and then taking those features and doing linear regression onto your targets. Okay, well, for a deep kernel machine then, I can come up with something very similar, at least at a high level. So again, I take the data here, then I put that into some sort of super flexible learned kernel that I don't know how to build yet. And then I'm going to use that super flexible learned kernel to do, let's say, kernel ridge regression onto some targets. Again, I could also have a Gaussian process at the output layer here if I wanted to. Okay, well, that's great, but it sort of pushed the problem downstream now. So I now need to know how to write down this super flexible family of learned kernels, and how am I supposed to do that? Well, so again, we're going to take inspiration from deep neural networks, and we sort of delve into how deep neural networks get this super flexible learned feature extract. And the answer, again, at a high level, is that they take in these low-level features, or sorry, they take the data, they transform it into some low-level features, and then they transform flexibly those low-level features into mid-level features, and then they flexibly transform those mid-level features into high-level features, and then they do linear regression based on those high-level features. Okay, so that is giving some inspiration about what a deep kernel machine should look like. So in particular, we should take the data and then transform it into a low level, and I'm now going to switch to using the terminology of a gram matrix rather than a kernel. So we take the data and transform it to a low-level gram matrix. Then we take that low-level gram matrix and we somehow flexibly transform it into a mid-level gram matrix. Then we flexibly transform it into a high-level gram matrix. Then we're going to use that high-level gram matrix to do this kernel ridge regression, or as the covariance of a Gaussian process. Of course, we've now pushed the question another step downstream, which is, well, how do I do these individual transformations, for instance, from a low level to a mid-level gram matrix? And so we know how to do that for a deep neural network. In particular, the features at one layer are going to be a linear transformation of some pointwise nonlinearity applied to the features of the previous layer. But we don't know how to do this in the case of a deep kernel method, and that is what I'm going to spend the next 3 slides talking about. How do we build these kind of gram matrix to gram matrix transformations that include the required flexibility? So yeah, we need this flexible learned function mapping from the gram matrix to a gram matrix. Okay. So the first step is to have a think about sort of kernel functions that we usually see and use. So most kernels take some features or some data and they transform them to a gram matrix. So for instance, I might have this. So my gram matrix for data point I and j here is given by taking the input vector, the ith input vector, so the input vector for training example I and the input vector for training example j, and applying some function. So this is a squared exponential kernel. So we have this Gaussian looking like form for that term in the gram matrix. So this is kind of a problem because ultimately what's going on is that we're transforming sort of either features or data to a gram matrix. What we really need to be able to do is to transform a gram matrix into another gram matrix such that we can then stack them. So what we're going to do then is to start by defining a data gram matrix, which is just this. So you can think about this as a dot product kernel applied to the inputs. And this G here is your usual kernel matrix-like object. So it's a training example by training example matrix. And now our key trick is that many kernels depend on distances. So up here, this kernel depends on the distance between the ith input vector and the jth input vector. It doesn't depend on any other feature of xi and xj. And it turns out that this distance can actually be recovered from this gram matrix. And so that then means that if I have a function here, kf, and that's going to take the whole stack of input vectors and return the gram matrix over there. So I can equivalently write this function as another, or I can equivalently write this gram matrix here that's output as a function of that input gram matrix here, because the distances can be extracted from G0. And it turns out that this isn't just true for these isotropic kernels that depend on distances. It's also true for a bunch of other kernels that we care about. And what especially matters are kernels from the infinite neural network literature. So this is where we are sort of explicitly deriving kernels that relate to what's going on in a neural network, and that, for instance, might arise from the application of Aurelian nonlinearity. Okay, you can try asking questions. I don't know if people can shout out if any questions come up. I'm happy to take questions during the talk anyway. So please do interrupt me if that is possible. I've not used this platform previously. Okay. So next, we're going to take that kernel function, which takes a gram matrix and returns a gram matrix, and we're going to apply it a bunch of times to get a deep kernel. Okay, so we start with that data gram matrix again, and we're just going to iteratively apply this function k to get a stack now of gram matrices, which I'm calling GL here. Now this is great because it's now deep. I have these multiple gram matrices, one for each layer. The problem is that it's not flexible. So in particular, remember that this kernel function could correspond to a squared exponential kernel, which would be this thing there. Now notice this thing has two hyperparameters. It's got capital A there, and so the sort of height of all of those kernels, and also the length scale, that L squared. So that means there's two hyperparameters per layer, and that means there's 2 times capital L hyperparameters in total. And that's fine, but it simply isn't enough to give you the flexibility for those complex data sets like images or sound. And if we think about deep neural networks, which are really the only model that we currently have that are able to be effective on those kind of data sets, then there's a huge amount of flexibility there. So normally there's more parameters than the number of data points, and there's simply no way that we're going to get the same amount of flexibility by having this very small number of kernel hyperparameters that we do here. So that leads us to step 3. We need to somehow add flexibility to this setup. So the game we're going to play is to encourage the gram matrix at the next layer to be close to the kernel function applied to the gram matrix at the previous layer, but we're not going to force equality. So we're going to start again with the data gram matrix, and then we're going to have this. So the gram matrix at the next layer is going to be close to, but not the same as this nonlinear transformation of the gram matrix at the previous layer. And then we're going to use that top layer gram matrix as the kernel, for instance, in a Gaussian process or in kernel-rich regression. Okay. So there are 2 approaches then to getting this close to, but not quite the same as relationship. So the first is a deep kernel machine. So in a deep kernel machine, we write down an objective, sort of like a regularizer, that encourages that gram matrix at the next layer to be close to the kernel function applied to the gram matrix at the previous layer, but doesn't require them to be exactly the same. The other approach is the probabilistic deep kernel process, which is actually turns out to be equivalent to a deep Gaussian process. And the idea here is to sample the gram matrix at the next layer from some prior over matrices with an expectation that is the same as this nonlinear transformation of the gram matrix at the previous layer. And if I choose this distribution to be a Wishart distribution, we're going to see a little bit of this later, then this deep kernel process prior is going to become equal to a deep Gaussian process prior. Okay. And then in both of these approaches, both the non-Bayesian, deep kernel machine and the Bayesian deep kernel process, we're going to include a term in the objective or the likelihood which encourages good performance on your task. So low mean squared error or good classification performance, for instance. And so then to see how this works a bit more concretely, we can write down the deep kernel machine objective. So again, what we do, we start off with this datagram matrix by taking the data multiplied by themselves. And then the objective function is this thing here. So then we can break it down into individual components. So first, these arguments to the objective function on the left are telling us that we're optimizing these intermediate layer gram matrices. So G0 here is fixed by the data, and then G1 to GL are the things we're optimizing. So then there's a term in here that encourages good performance. And so that depends on our targets Y, and it depends on that kernel function applied to the top layer gram matrix. And this could potentially be the log marginal likelihood of your Gaussian process, but it could also be a performance measure in kernel ridge regression or in, say, a support vector machine. So then we've got this bunch of terms that encourage the gram matrix at the current layer to be as close as possible to the kernel function applied to the gram matrix at the previous layer. And you can see that it does this because this is a KL divergence applied to a multivariate Gaussian with that gram matrix as the covariance, and a multivariate Gaussian again with this kernel function applied to the gram matrix at the previous layer as the other distribution. So this KL divergence is then going to be better. It's going to be as close to zero as possible if these two matrices are similar, and it's going to get bigger as those two matrices become different. And then there is this constant here, nu L, which is going to control the degree of regularization. And it's called nu L here because intuitively it behaves an awful lot like the width of a deep Gaussian process. So you can sort of think of it in those kind of terms. And certainly we're going to choose nu L to have values that are kind of 20-ish, let's say, rather than like 0.001 or 10 million. Okay. So that's the sort of very big picture overview of what's going on in a deep kernel method, how I might define one. So now I'm going to talk about 5 sort of reasons we might want to care about these deep kernel methods. So first, interpretability. I'm going to argue that deep kernel methods are much more interpretable than corresponding deep neural networks. 2, unimodality. I'm going to argue that the loss function is for deep kernel machines is actually unimodal, and that's going to help us a lot. 3, I'm going to argue that structure in the loss landscape for deep kernel methods might be exploited to give us fast optimizers and solvers, potentially even faster than what we can get in the deep neural network world. 4, it turns out that deep kernel methods have really profound connections to the theory of deep neural networks, and I'm going to outline a little bit how that connection works. And then 5, I'm going to talk a little bit about those Bayesian deep kernel processes that I mentioned a couple of slides ago. Great. So first then on to interpretability. So as I'm sure you're all aware, there's a bunch of work now on trying to understand what neural networks are doing. And for instance, what you might do here is to try to understand the function of an individual unit in the network or an individual weight in the network. And this is actually something that neuroscience has been doing for an awful lot longer, because as a neuroscientist, you tend to be able to only record one or a few cells in that circuit. Now, the issue is that, well, neural network units or weights, I would argue, are inherently non-interpretable. If you look in your network and you discover that one particular unit fires to trees, it doesn't really tell you how the overall circuit is operating. It doesn't really tell you why the sort of top layer output of that network is a particular thing for a particular image. It's not really clear it tells you very much. And certainly this is sort of borne out in some of the interpretability methods for neural networks, which often end up being somewhat superficial. So they might, for instance, say that in making this classification, the network focused on this area of an image, which is kind of fine. But again, it's not really clear that that tells us what we want to know about why the network is giving us a particular output and how the network is sort of working underneath. But I would argue that kernels give us a much better grasp on interpretability. And that's because kernels are inherently interpretable. So they measure the similarity sort of as judged by the network or by the model of any two inputs. And that's something that sort of I as a human can get a handle on. Okay. And because deep kernel methods kind of work fundamentally in terms of these kernel methods, they don't have units, they don't have weights at all, then I would argue that kernel methods are inherently much more interpretable. And I think there's a lot more work to go into to really nail down exactly what it is that makes kernels more interpretable, exactly how we can sort of get that interpretability payoff in kernel methods and deep kernel methods. But I definitely think this is the way to go, as it were, in comparison with just sort of banging on about neural network units and weights, which I think is maybe a bit of a lost cause. Please do argue with me afterwards if you disagree, though. Okay, so that was interpretability, a bit more sort of concrete and technically. Let's talk about the unimodality, or the number of modes. And so we know that neural network loss landscapes are hugely multimodal. This is a picture of a loss landscape from past work. And you can see that this is going to cause lots of problems. So the first is that it's going to be difficult to optimize on this loss landscape effectively. So not only might you get stuck in local optima, but also if you want to come up with a sort of cleverer or a more sophisticated optimization method, typically it's going to work well if you've got a simple loss landscape that's maybe unimodal or convex. But we can see that essentially this loss landscape has zero nice properties at all. It's not unimodal, it's not convex, it's just really nasty. What that means is that I typically get very little payoff, or relatively little payoff anyway, from going to sophisticated second order methods. And so instead, what most people do is they stick with stochastic gradient descent, and they sort of accept that stochastic gradient descent is slow and that you're going to have to do lots of hyperparameter tuning to get it to work well. The next issue is that it's difficult to approximate or sample the posterior overweights that this loss landscape implies. So if you imagine trying to approximate this as, let's say, a Gaussian or a quadratic, simply isn't going to work very well because this loss landscape is hugely complex. And that's going to make it very difficult to do something like variational inference for your weights in a Bayesian neural network accurately. And finally, if you're a statistician, and I sort of, one of my missions anyway is to try to bring machine learning and statistics much, much closer together, then many of your proofs are going to care about identifiability. And this, it is inherently non-identifiable for many reasons, essentially the multimodality. All right. So what is the problem here? Why does this horrendously complicated lost landscape arise? Well, at least one source is from permutation symmetries. So let's consider this little slice of a neural network here. So this is the input layer, this is the output layer, and this is the intermediate layer. And now these blue connections and the blue elements in these weight matrices indicate a negative weight, and the red connections indicate a positive weight. So now what I'm going to do is I'm going to swap the identity of those middle two, those two units in the middle layer. I'm going to swap those over. Now you can see that the weight matrices, when I do this, change. But the input-output mapping of the network stays exactly the same. Basically because these downstream units are just summing those inputs, and we have essentially the same units there, it's just they're in different locations. And so that means we have the same input-output mapping, but different values of the weights. And that's kind of constituent of these permutation symmetries. So if I take like a mode of the network, which might be, so this setup of the weights might be a mode, well, that means that this setting of the network also has to be a mode because it's got exactly the same input-output transformation. And therefore, this lost landscape must be very, very, very complicated. And in fact, it's got sort of the number of modes of permutations of those intermediate layer units, which is very, very, very large. In contrast, let's think about what happens with deep kernel machines. So it turns out there's actually a proof of unimodality in the linear case. And it turns out this is quite instructive, so it's worth thinking a little bit about it. So a linear deep kernel machine is one where this kernel function just returns the gram matrix from the previous layer. So this corresponds very closely to a linear neural network, which is why I call it a linear deep kernel machine. Right. So in this case, it turns out the only solution or the only optimum of those intermediate layer gram matrices is given by this functional form here. It looks like it shouldn't be symmetric. It is by complicated mathematically things. I definitely had to go and check it in Python to make sure it really was symmetric. But the key idea here and the key thing that I want you to extract is that ultimately, oops, sorry, there should be a -1 in here. There should be a -1 on that G0. Ultimately, this is interpolating between G0 here and G of L+1. So if we're at here low layers, so if this little l is say 0 or 1, then the gram matrix is going to be close to that input gram matrix. And if L is now much larger, so we could think of L being then very close, little l here being close to capital L, then this gram matrix here is going to be very close to the output gram matrix, which is defined by this relationship here. So you can think of these as interpolating then between the input gram matrix defined by those input vectors and the output gram matrix defined by that sort of the same matrix, but now for the targets, the y's. So that is sort of very instructive theoretically as to what's going on, point one. Point two, we can prove there's only one of these solutions, and therefore deep kernel machines, or the deep kernel machine objective, is then unimodal, at least in the linear case. Then in the non-linear case, things are obviously more complicated. We've tried lots of proof strategies. Turns out everything's very hard, perhaps won't surprise you at all. Instead, we, or in particular my PhD student Adam, did a bunch of experiments. And so he took all of the smaller UCI data sets, he considered 1- and 2-layer networks, he considered 2 different types of kernels, he ran it for absurd numbers of gradient steps on the full data set, by the way, so this is 200,000 epochs. And he basically found that it always converged to the exact same answer. So here, the different colors are different initializations. We can see that the spectral norms and various projections converge to the same value. And then we can also compute the average Frobenius distance between the optimized gram matrix for each initialization, and that distance is going to 0 as those gram matrices all converge on the same solution. So this gives us pretty good confidence, actually, that the deep kernel machine objective is unimodal. And it also turns out that other closely related objectives that sort of aren't quite our deep kernel machine objective, so they're not unimodal. And I think that's very interesting because it does suggest there's something kind of fundamental in the deep kernel machine objective that other potentially sensible objectives aren't getting at. Okay, so what then are the implications of unimodality? If we were talking to machine learners sort of 20 years ago, I really wouldn't need this slide, but given the success of neural networks, people have kind of forgotten about why unimodality is desirable. So first, there's the potential to develop clever, potentially second-order optimizers that can exploit this structure. And second, from the Bayesian perspective, if I've got a unimodal true posterior, it's going to be much, much easier to accurately approximate that than if I have a highly multimodal true posterior, in which case it's essentially impossible to get a good, let's say, variational approximation. Okay then. So let's try to get a bit of this payoff by thinking about faster matrix solvers or optimizers. So to understand a little bit what's going on here, again, or how to develop such an optimizer, I'm not going to go into the full depth of how we get there. I really just want to give you a flavor. We can again consider that linear kernel, so this one here. Now what I'm going to do is to solve for where the gradient of that objective is 0. I'm going to do some pre-impulse multiplication here to make the exact form slightly simpler. And so it turns out that then if I want to set the gradient with respect to this particular gram matrix to 0, then this is the expression I have. So I'm now going to think about doing coordinate descent. So I'm going to solve here for GL with fixed previous gram matrix GL minus 1 and fixed subsequent gram matrix GL plus 1. So this is now a matrix quadratic equation. So there's one GL here, there's two GLs there, and there's no GLs on this side. And it turns out that this is actually an equation that, well, we as machine learners probably don't know how to solve, but control theorists do. So this is called a continuous algebraic Ripatic equation, and it's very well studied in the control theory literature. And they, in fact, give us a huge number of different solution strategies, and they range from exact or closed form methods based on an eigendecomposition of an extended matrix through to Newton's methods, which tend to be faster, but then they're iterative. And it turns out that then all of the
Laurence, can I just interrupt you? And it's also related to a clarificatory question asked in the chat box.
Yeah, sorry, I can't see them, so you feel free to interrupt me to
yes,
yeah.
Yeah, so it's actually, they're asking if they should be KGL equal to GL minus 1, and it's, so is K, otherwise, is K just unity transform
Yes.
or something?
Sorry, this top equation is correct.
Okay, so could you clarify how this works? Because it seems that K doesn't do any transformation, and
Correct.
we just get back the same thing.
Yes. So in essence, what I'm doing is, in essence, the deep kernel machine combines those two steps. It combines this deterministic nonlinear transformation, which here is the identity, I agree, but usually it would be nonlinear. But then it also adds flexibility in that, for instance, objective. So when I take that linear kernel here, I'm essentially including only flexibility and not any of those deterministic transformations. I mean, potentially another answer is that in a practical network, I will always have a nonlinear k. The linear or the identity k here is really just to facilitate analysis. But when we're actually doing stuff with this approach, we do use a nonlinear k in here. It can be adapted to the nonlinear case.
So in the linear case, you already mentioned in the probably the previous slide that yeah, not this one, the one before, or even where you said that as L, the small little l goes towards 0 or towards capital L, you tend to interpolate between G0 and G capital L. So how would that work if K is just unity, or I mean the unitary unit? Yeah.
Because there's two things going on. So if we go all the way back here, you're right. It would be, nothing would be going on, because here, the Gram matrix of the next layer is equal to that nonlinear transformation of the Gram matrix of the previous layer. But I'm not doing that. I'm setting the Gram matrix of the next layer close to, but not exactly the same as that nonlinear transformation of the Gram matrix of the previous layer. And there's two ways of getting it close to, but not exactly the same. So I could define an objective that encourages that Gram matrix to be close to this guy, but not exactly the same. Or I could sample the Gram matrix from a prior, which is somehow centered on this nonlinear transformation. Then in both of those cases, the Gram matrix at the next layer isn't going to be equal to the Gram matrix at the previous layer, even if I've got a linear kernel, or k just returns GL minus 1.
Thanks a lot. Yeah, that clarifies everything.
Okay, yeah.
Yes.
And so again, in this objective here, it encourages the Gram matrix of the next layer to be close to that transformed or potentially not transformed Gram matrix of the previous layer, but it doesn't enforce they're the same. And that flexibility is then really important because it gives us some flexible learning of the good representations for those complicated data sets, things like images or sound, those examples we had at the beginning. Yeah, and again, it should also be said that that linear kernel is not actually very useful in practice. We're only using it here as a guide to work out what kind of optimizers we should be using. And in particular, it's only when we use this linear kernel that we get this beautiful fact that we can solve for the optimal Gram matrix at this layer, given the Gram matrix at the next and previous layers. And so that is something that you can't do essentially in any other setting, to my knowledge. And that then can be adapted to the nonlinear case, and you end up with a solver or an optimizer that converges potentially very rapidly. So in our experiments, it seems to converge in about 10 steps, which again is now sort of expected because we have this coordinate descent or ascent type structure rather than just slow gradient descent. And this is also very exciting because it means that there is structure in deep kernel machines that we can exploit that potentially gives us the possibility to beat sort of neural networks at their own game, at least here if we're talking about training time. Okay. So then fourth, it's also worth thinking a little bit about connections to deep Gaussian processes and Bayesian neural networks. Because I think this connection, and it's mainly theoretical, also gives quite a lot of power to the deep kernel machine setup. So it turns out that the deep kernel machine, if you set it up in a particular way, does exact inference in an infinitely wide Bayesian neural network or deep Gaussian process. And then these deep kernel machines actually become an ideal theoretical model for that neural network or deep Gaussian process. And the reason is that they capture representation learning, so they capture that shaping of the top layer representation or features so as to get good performance on those complicated data sets. And that's really kind of the essence of deep learning. But at the same time, they're very simple. And so I strongly suspect, anyway, that in this limit where the deep kernel machine is equivalent to these infinite Bayesian neural networks, then the posterior is actually multivariate Gaussian. And so that gives us then a lot of simplicity in terms of the sort of theoretical structure of those networks, and it makes it much simpler than trying to work with representation learning in finite neural networks where you don't get these very nice properties. All right. And so to be a little bit more concrete, there's just one slide on this about how to draw this connection from Bayesian neural networks or deep Gaussian processes. So in a Bayesian neural network, we have this form. So F is the features at one layer. That's going to be a matrix with the number of, which is features by training inputs. And then we apply a nonlinearity and then a matrix there. Okay. And then a deep Gaussian process looks very similar, or it doesn't really look similar, but it turns out to be quite similar in the sense that we take some features, we transform them with a kernel, and then we use that as the covariance of a Gaussian for the features at the next layer. And this F here is then a vector of all training input points. So this is kind of the activation of one unit for all training inputs. And in both cases, the equivalence arises by taking the Gram matrix here equal to the product of those features with themselves. So this is then a very simple, and it's exactly analogous to these definitions of the input and the output Gram matrix that we saw earlier. And in fact, the way of deriving that deep kernel machine objective arises from this viewpoint. So you define the deep kernel machine objective as either variational inference, or you can also actually do it as Langevin sampling in such an infinite neural network or deep Gaussian process. And I think that's sort of that connection to inference is why the deep kernel machine objective has such nice properties and such a nice form. Okay. And then finally then, it's worth talking a little bit about those deep kernel processes. So that Bayesian or probabilistic form. And this is actually where we started with those two papers down there. So the idea is that we're sampling a Gram matrix from a distribution over positive definite matrices. So again, we start with this G0, and then we're going to sample now, sort of iteratively or recursively, the Gram matrix at one layer based on that nonlinear transformation of the Gram matrix at the previous layer. And you can again incidentally see that even if this K here just gave you back GL minus 1, that GL here would still be different from GL minus 1 because GL is being sampled from this distribution. It would just be a distribution that is centered here on GL minus 1. And then, because we're in a probabilistic setting, we would take the output or the targets to be distributed according to a Gaussian or a Gaussian process with a kernel, which is then that kernel function applied to that last layer Gram matrix. And it turns out that this is equivalent to a deep Gaussian process where we do this, where we sample the features from their Gaussian depending on the kernel of the depending on the features at the previous layer, and then compute the Gram matrix like this. And it turns out basically that the definition of the Wishart distribution is samples from this generative process down here. So it's sort of almost a trivial connection at this point anyway, but it's certainly a connection that hadn't been realized previously in the literature. Okay, so then what actually sort of happens with those, with that generative process? What does it look like? Well, we start off with some inputs, x, which I'm not drawing, and then we're going to get some base kernel, which I'm going to call here k0. And if we think about this as squared exponential, it might have this form. So nearby inputs are similar, distant inputs are less similar. And then we're going to sample that gram matrix. Because we're sampling from a distribution now, we're going to get some variability around k0. So that's going to look something like this. And then we're going to transform it again by putting it again through a squared exponential kernel. So here blue is actually positive and white is 0, red is negative. And so the squared exponential kernel gives us all positive values, which is why this is then blue. And then we're going to add some more flexibility again there by sampling again from that Wishart, transform it, and then use this as the kernel for a Gaussian process at the output. And we can do this with a Wishart distribution over matrices. Turns out there's other choices that work as well. One is an inverse Wishart here, but you can see that this has a very similar intuition. It's just that the noise has a slightly different structure, which is not something that we've gone in and investigated too much. Okay. And then with these things, it turns out that you can do something very similar to doubly stochastic inducing point variational inference in a Gaussian process. And we do that by defining an approximate posterior over these gram matrices. And again, I'm not going to get into this in depth. I'm just going to show you some results from UCI data sets.
Sorry, Laurence, can I ask you something?
Yeah.
So in the previous slide, it's still not clear for me. How do you go from G1 to K1? So these G1 are positive semi-definite matrices that you sample from your Wishart distribution.
Yeah.
How do you use those to actually compute K1?
Yeah. So this gram matrix corresponds to these features.
Yeah.
Okay. And then when I compute my squared exponential kernel, what I care about is distances between these features.
Mm-hmm.
But then I can compute those distances just from the gram matrix.
Mm-hmm.
That's the trick. That's it.
Okay.
So then I start with the gram matrix, compute the distances, compute the squared exponential kernel.
Uh-huh. Okay. 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 Thanks.
Right. So then that's kind of it for the main body of the talk. So now it's just worth thinking about some questions and some sort of ideas that we're thinking about at the moment for future work. So kind of in practice, it's going to become very important to, so I showed you some of these ideas for getting that fast solver. We also, however, need to make that scalable, for instance, by using random Fourier features. So that's something we're working on at the moment. So that could be very exciting and really give us huge speed ups in our ability to learn these deep nonlinear function approximators. Then, you know, we want to compete with neural networks, so it'd be great to see if there's a convolutional variant of these methods that actually works well. And, you know, building up towards eventually competing with neural networks. Then on the theory side of things, we still have this question of, is the objective in the nonlinear case actually unimodal? I'm really excited as well about using these kind of ideas, these working with gram matrices, to understand both neural networks and actually brains. So there's a lot of work in neuroscience at the moment where they actually use what they call representational similarity matrices, which are basically end up being these gram matrices or these kernel matrices, to understand whether measured data is similar somehow to a convolutional network. And I think it's interesting to ask whether we can actually formulate a theory of neural representation in the brain actually using these matrices themselves, rather than just using them as a kind of measure of similarity. I'm very interested in whether there's some way to get generalization bounds in these deep kernel machine formulations. And it seems like it would be a very convenient structure to start doing that, again, because it's much simpler and potentially much more mathematically tractable than the complicated multimodal deep neural network mess. All right. And so then, I thought it was worth just describing quickly what papers there are and pointing you in the direction of what you might want to look at. So this was kind of the first paper that doesn't involve any deep kernel machines, but lays a lot of the groundwork. So it kind of uses kernels to analyze the flexibility in finite deep neural networks. And it builds a lot of the intuitions that deep kernel machines ultimately use. Then this paper introduced deep kernel processes. Turned out that the probabilistic deep kernel process came about first, but it actually only used these deep inverse Fisher processes, which aren't equivalent to deep Gaussian processes. So then at NeurIPS this year, just got it accepted, we developed a new method for deep Wishart processes, and those are interesting because they are actually equivalent to a deep Gaussian process. And I'd recommend the background section in this paper as the best starting point for further reading. And that's because we were trying to sort of show too many almost equivalences in this deep kernel process paper, so it became a bit messy, whereas this one is a bit cleaner and it just kind of focuses on the connection to deep Gaussian processes. And finally then, we've got a very early version of the work on deep kernel machines and fast solvers up on archive. Great, thanks. And these are the two without whom, all of this work would have been very difficult. Right. Hello?
Yeah, thanks, Laurence. I'll just clap for the audience.
Oh dear. All right, stop sharing. There we go.
Thanks, Laurence. Are there any questions? Oh, we have actually two questions, no? Yeah, there is one by Tom and one by Mike. Do you have access to the questions, Laurence? They're a bit long.
I do, yes.
Yeah, okay.
The performance improvement for the deep kernel process over the deep Gaussian process on the UCI data seemed especially pronounced for the smaller data sets, and the gap is smaller for the bigger ones like protein, for example. Is this because the complex multimodal posteriors in deep Gaussian processes are more challenging to approximate in a small data regime, whereas the simpler posteriors in the deep kernel processes don't have this problem? So it's a great observation. We do see bigger benefits in the smaller data sets. And my guess is that the reason is actually quite simple. It's that in the large data sets, we basically find the right function. So modeling uncertainty doesn't matter. All that matters is, does your model somehow have the flexibility to capture that right function? Whereas in the smaller data sets, modeling uncertainty matters, and deep kernel processes model that uncertainty better. That's definitely our intuition. And then from Mike, although you've pointed out all the issues around deep neural networks, is there any sign that if you compute maybe numerically the correlations in the inputs and outputs to each layer of a deep neural network, is there some sign that deep neural networks are doing something like this? So thanks, Mike. I mean, absolutely, like a lot of this stuff started in that first paper, which was just an analysis of what deep neural networks are doing. And so in particular, that work kind of started out by analyzing infinitely wide neural networks. And typically, unless you're very careful, infinitely wide neural networks don't display any representation learning, whereas finitely wide ones do. And then that paper kind of analyzes exactly what kind of representations, kind of kernels, might we expect to come out of those deep neural networks. So it developed then a lot of the linear theory that I showed you. So that was really developed for deep neural networks. And it turns out again that deep neural networks have this property that the top layer representation is very similar to that sort of YY transpose, that output kernel. So if you actually sort of look at the spectrum of the top layer representation in a CFAR10 network, that's going to have 10 dimensions. And those 10 dimensions basically correspond to the 10 class labels. And it throws away all other information. And that's exactly what we'd expect based on the linear theory. So yeah, I realized that explanation was probably a bit scattered, but the big picture there is definitely that a lot of this stuff was developed to think about deep neural networks and to theoretically analyze deep neural networks. And it's only as an extension that we're playing around with them as kind of machine learning approaches in and of themselves. So I think that's really the novel thing in the deep kernel machine, or the deep kernel method approach, is that can we take this theoretical stuff for deep neural networks and kind of treat it as its own thing, and see how well it works in its own world.
Okay, so I think we don't have more questions. So
Maybe Mauricio, I could go and ask one.
oh, yes, Aditya, yeah, of course, yeah,
Yes.
yeah.
So Laurence, thanks for the great talk. You already mentioned that there could be some connections, say, or at least way to interpret, say, for neuroscience, these kind of representation that may develop. Would one also not then require, doing the full circle, as in coming up now with a neural network implementation of these? Or would this not be possible because, neural networks have this problem of this permutation problem that you just told us about?
Well, I mean, so again, there is this. So again, because a lot of this theory really comes from the analysis of deep neural networks, it is actually an appropriate tool to use. So what that connection says, if I have my activity of my neurons, so I have it as a big matrix with training examples by neuron here. So I can get a gram matrix by multiplying that matrix by itself transposed, such that I end up with a training example by training example matrix. So that's the behavior of that object is what all of these deep kernel methods talk about. And in fact, most of them talk about it, most of them are grounded in their underlying neural network model. So it's not like they've gone away into their own world. They really are just, for instance, describing the behavior of those or behavior of that network in terms of those gram matrices. So it's just, yeah, I'm experimenting with how to present this stuff. At the same time, there's a whole bunch of people in neuroscience, though, like Nico Kriegerskorter, like Dan Yammins, like James DiCarlo, who use these matrices, which they sort of call representational similarity matrices, as ways to compare what's going on in the brain with deep neural network architectures. So there's an awful lot of work in neuroscience on that, and the kind of game to play is to ask, well, can we go further than just comparing my convolutional network with my data? Can I actually say that, well, the theory of the brain should contain an awful lot of these similarity matrices? So that's kind of what the direction that we're pushing on that front at the moment. And I think it's quite an exciting avenue because it gives you this intermediate layer view between units where you can't see what the network is doing and the high level like behavior where, again, you've got no access to what's going on in the network. It kind of gives you a nice intermediate layer viewpoint, which I'm hoping is going to be quite valuable.
No, thanks for that. That clarifies. But also, just to push you a bit more on that, but ultimately, the brain does have a neural network. So, do you think so? I mean, it's great that you look at these representations in themselves without bringing the units into the picture. But then you kind of mentioned that your current implementation doesn't have any units and no weights. And so, would you need, or is there a way to actually implement this using a neural network?
Well,
And compare
so
those as
one
well?
way to view what's going on is that there is a neural network. It's just a big neural network. And I'm using, and you can use the deep kernel machines to describe the behavior of the representations in that neural network. So it is, in many senses, in many formal senses, the gram matrix view is a complete view of what's going on in the underlying neural network. And certainly that's where an awful lot, so that's where that initial paper came from. It was entirely thinking about how to understand deep neural networks using kernels as tools. And it's only kind of subsequently that that theoretical picture that we've kind of pushed then, trying to take that away from neural networks and treat it as its own machine learning method. But like ultimately, there is this very, very deep and strong connection to the underlying neural network that a lot of the methods came from.
Right. Yeah. Thanks. Laurence.
Thanks.
Okay, thank you. Probably we finish here, and thanks, Laurence, for your time and for the great talk. I'm just gonna put here on the chat the link that Laurence gave us, in case people want to book a meeting with you and talk about the research you're doing. So you can book meetings for 15 minutes or 30 minutes, or I think even an hour. So
15 or 30.
so that's really useful, and thanks again for your time.
Fantastic. Yeah. Thanks. And thanks for the great questions.
Yeah. Have a nice day, everybody. Bye bye.